This is section 11.8, part 2, and we're going to be looking at parameterizing with respect to arc length. In order to understand what we mean by this, let's consider two interesting questions that we might ask about a graph like this. If this is our curve r of t, in both situations, and we have some starting point, so let's just assume that this point corresponds to t equals 0, again on both graphs. Then I might ask you one of two questions. I might ask, if you start at this given point and walk for a specific amount of time, where do you end up? That's actually a pretty easy question to answer. Since we're starting at time 0, all we'd have to do is plug in the new time, and that should give us the position at that time. So, question 1, pretty easy to answer with what we already know. It's simply r of our ending t value. And that's going to give us the ending position. So not a big deal at all. If I said where are you going to end up if you walk for 4 seconds, you would simply say, okay, what's r of 4? And we'd know that we walked along this path and that we ended up at that location. Now, the more complex question to answer is question 2. What if I tell you that you're going to start at the given point and you walk for a specific distance? So instead of saying you're going to walk for 4 seconds, what if I say you're going to walk for 4 meters or whatever the distance units happen to be? Now where are you going to end up? Well, we don't have an easy way of answering that question based on what we already know. Our goal is to say, okay, if we walked along this curve a total of 4, let's say, meters, then what's the location of the point that we end up with? That's what we're going to investigate in this part of the section. So, question 2, again, much more difficult to answer right now. It would actually be a lot easier to answer that question if we could express our function r in terms of distance rather than time. If we had a function r of a distance parameter instead of r of a time parameter, then that could be just as easy a question as the first one was. So that's what we're going to work toward. To do this, I'm going to start by defining essentially an arc length function. S of t is the integral from a starting point A to some generic ending point t of the magnitude of r prime of u du, and this is our vector valued function r. Notice we're integrating a speed function, so we're getting an arc length, and it would be the length from the starting time a to some general ending time t. So it measures arc length, which is really just the distance along the curve, from t equals the starting point A to t equals some sort of generic ending point. All right, u, by the way, is what we call a dummy variable. We can't use t as the limit of integration and also use t in there, so we just changed the t's to u's. Don't get too worked up about that. It's just a dummy variable. This is going to define s as a distance variable. So what I'll end up doing is after I figure out the value of this integral, I'm actually going to solve this for t, and then I can replace the t's with s's. And I'll have my r function, my initial position function, given in terms of s, a distance parameter. So, step by step, how does that look? To parameterize with respect to arc length, I'll begin by evaluating that integral, s of t, integral from a to t of r prime of u du. I'll solve the resulting function for t in terms of s, and then I'll just substitute for the t's to get a formula for r of s. So let's try it out. I'm back to my helix again. 3 cosine t, 3 sine t, t represents our trajectory, and I'm telling us let's assume our distance units are meters. My starting point is going to be t equals 0. Notice if t is 0, I'd get 3 cos 0 is 3, 3 sine 0 is 0, and t equals 0. And my question is, where are we going to end up? First of all, if we walk for 4 seconds, and then secondly, if we walk for 4 meters. With what we have right now, the first question is easy. The function is parameterized with respect to t, and I gave you a t value. So this one is as simple as just taking r of 4, 3 cosine 4, 3 sine 4, 4. Make sure you're in radian mode here. And that's going to give me approximately negative 1.96, negative 2.27, and 4. All right, what if instead I now say, let's start back at this point again, but where am I going to end up if I walk for 4 meters? Now instead of giving you a t value, I've given you an s value. So to answer this question, I'll need a function r of s instead of r of t. To get that, I'm going to follow these steps up here in my parameterizing with respect to arc length. So first of all, I need to evaluate the integral, s of t. It's the integral from the starting time, in our case we're starting at t equals 0, to a generic ending time t, since we don't know when we end yet, of the magnitude of r prime of u. So I'm going to try and do 2 things here. I'm going to take the derivative and substitute the u at the same time. So my derivative would be negative 3 cosine, and that'll become a u. I'm sorry, that should have been negative 3 sine, because I can't do 2 things at once. There we go. Derivative of cosine, negative sine. This one becomes 3 cosine u, and the derivative there is just going to be 1. So that's my r prime of u. Magnitude of that is the square root of 9 sine squared u plus 9 cosine squared u plus 1. Sorry, that was a du. And again, that's just 9, since sine squared plus cos squared is 1. So 9 plus 1 would be the square root of 10 du. And integrating that is going to give me the square root of 10 times u from 0 to t, or square root of 10 times t. So that's now an expression for s. Step 2 said solve this function for t in terms of s. So s over the square root of 10 is equal to t. And I'm now going to replace all the t's in my original position function with s over the square root of 10. R will now have the parameter s, and it will look like 3 cosine instead of t, s over the square root of 10, 3 sine, s over the square root of 10, And then the last parameter, last position is t, which I'm just again replacing with s over the square root of 10. I now have a position function for r, but it's parameterized instead in terms of this distance variable, s. So since I know how far I want to walk, if I now just plug s equal 4 in here, I can figure out where I'm going to end up. And of course I could do that with any distance I wanted to walk along this curve. We just happen to have been asked to walk 4 meters. And that just becomes a calculator problem again. And let's see, when I did plug that in my calculator, I got about 0.90, 2.86, and 1.26. So let's think about this geometrically for just a minute. Remember that we started with our helix, right? We know what that looks like. Let me sketch it. We start at the point 300, and then we know our helix goes around and up, like so. We discovered that if we walk for 4 seconds, we ended up at this point. Looks like third quadrant and then up 4. So about roughly -2, -2, 4. So there's about -2, -2 was actually -2, -2.27, so maybe I should have gone a little bit further over on the y. And then I go up to the point on my helix. That has to be a z value of 4. And that's where I end up. So if I walk for 4 seconds, I'm going to follow that path. Now, if I walk instead 4 meters, I was told that I'm going to end up at 0.9, 2.86, 1.26. So let's see, x is 0.9 about here, y is 2.86, so almost 3, maybe around there. And I'm going to be at roughly this point on my graph. And so if I walk for 4 meters, I'm going to follow this path. All right, that brings us to the end of section 11.8.